All right, so welcome to another episode. Today we are going to look at how we can tackle first order homogeneous differential equations. Today is going to be so fun. We are going to dive into homogeneous functions and understand how we can work our way out when we have a function and it possesses the features of homogeneous, how to identify it, how to know how to work it out and make it so simple for you to separate it and integrate it to uh, the desire. All right, so let's dive into it. So here, for a function to be differential or a differential equation is called homogeneous if it is written in this form. All right, so if it has this function and m of x and y dx plus n of x and y dy equals 0, then we call it a homogeneous function, all right? Where both m of x and y and n of x and y are equal to are homogeneous functions. Okay, so and they all have the same degrees. They must not have different degrees. They must have the same degrees for them to be able to be classified as a homogeneous function. Okay, so that means we can have a variable, say t, combined with each of the function, and if they are able to come out completely, or if they are able to be factorized completely, then we call it a homogeneous function. All right, so here we have m of tx comma ty is equal to t power n, right? T power n here means that for some integers n, it can be any number, it can be 2, it can be 3, it can be, of course. Okay, so the same thing applies to a n of tx dy equals t power n on x and y. Okay, so these are the steps involved in transforming them or a function into a separable form. You know, all these homogeneous stuffs, the idea is that we want to transform it into a separable form so that we can integrate them. All right, so the function has to be in this form for it to be homogeneous. Okay, so we have differential of a function, two variables with the same degrees. They are all having the same degrees. Okay, and that should be equal to a function of x or a function of y on x. All right, so that is the form of a homogeneous function, a function of y on x. So this y on x here, we will represent it by a variable called v. Okay, so we have to transform that form, this function, into a separable form. Okay, so here, before we can transform this into a separable function, we have to use what we call the substitution method. Okay, so don't forget, if your integration techniques are not really sweet, please check out my link. We have integration by part, integration by substitution, by partial fraction, all of them are there. Watch it out and you will have differential equations. Okay, let's go. So this is how we transform the homogeneous function into a separable form. Okay, so first, let v equals a variable which is the y on x. Of course, you had the y over the x equals a function of y on x. So first, let v equals y on x. That is the first thing you have to do to be able to transform the function from homogeneous to separable. for easy integration. Okay, so once you have it, you can say that this implies that y is equal to Vx. Okay, so this we have here means that wherever we see y, we can replace Vx. Okay, and this also symbolizes that we have two functions multiplying, so we can do what we call differentiation by product rule. Okay, so when we do that, it means that y equals Vx, applying the product rule on this, then we are going to have dy dx equals, we maintain the fact, or we differentiate the first function, which is the v, with respect to x, then we maintain the second function, which is x. Okay, plus we maintain the first function, then we differentiate the second function with respect to x. So the x over the x. Okay, so we have x dv over the x plus this takes of this, so we have v. So this becomes the differential of y equals Vx. You have to know this offhand all the time you apply it. You don't need to be differentiating all the time. So you know that y equals Vx. When you differentiate, you have x dv over the x plus v. So you do your substitution in there and then you go away. So this here, we have dy dx equals x dv over the x plus v. We do that substitution in place of this. Okay, so once we have that, it means that we are going to have x dv over the x plus v is equal to a function of y on x. Okay, so this will be equal to this right here plus v equals a function. We know that y on x is, of course, v. So we have a function of v. So this we have right here, you can see that we can do something about it and we will be able to separate it. Okay, so this right here, we can send this here, bring this here, and okay, so we have here x dv plus v equals x dv over the x is equal to f of v minus v. Okay, so this we have right here means that all these functions are of the same variable, right? So we have this goes this place, so we have x dv equals f of a function v minus v dx. You want to separate the variables, so this x moves to this junction, and then f of v minus v comes to this junction. So we are going to have 1 over f of v minus v. Okay, dv. That should be equal to 1 over x dx. So here we have been able to separate the variables into the separate components. We have separated them into different components, right? So we have v functions here, a function of v in terms of v only, and then a function in terms of x only. So now, because we have been able to separate them, we can integrate with ease, right? So integrate this section, then when you are done, plus your constant of integration, then you integrate this section. Most times this section involves you have to apply integration techniques. Of course, I have them down there, so don't forget to check out the link and enjoy those lessons as well, by parts, by partial fractions, and by substitution, of course. So here you differentiate, you integrate this. You can either use by partial fraction or something. Then, if possible, you make the variable v the subject. Don't forget that v was represented by y on x. So when you are done, then you do that substitution and make y the subject, if possible. If possible. So this we have here. Let's dive into it and look at an example, a work example under homogeneous. Okay, so let's look at this problem to clarify the homogeneous method. Okay, so this here, you see we have x, a function combined with the differential, which is dy dx. Okay, so we try to avoid this here by dividing through by xy. So this takes of this, so you have dy over dx is equal to x minus y all squared. You know, this can be like this, xy over xy. Okay, so this we have dy dx equals x minus y all squared over xy. Okay, plus xy over xy is positive 1. Okay, so now we have this function. What do we have to do? We have to apply what we call the substitution method. Okay, so here, let v equals y on x. Okay, so if that is true, then we can say that y is equal to vx. So as usual, when you differentiate this, you are going to have dy dx equals v x dv over dx plus v. Right? So this, we are going to do this substitution in place of dy dx over here. So when we do that, we are going to have x dv on dx plus v, and that should be equal to this function, right? X minus y all squared over xy plus 1. Okay, so this is what we have right now. What do we do next? So here, we are going to have x dv over dx plus v. That should be equal to x squared. We are expanding this bracket, minus 2xy plus y squared all over xy plus 1. Okay, so here, what can we do? We have this here, we want to separate the variables. So we said that Vx is equal to y. So wherever we see y, we can do this substitution. So let's substitute Vx in place of y. Okay, so when we do that, we are going to have x dv over dx plus v equals s squared minus 2x into vx plus vx all squared plus 1. All right, all over x into vx all squared. Okay, so we have x dv over dx plus v. That should be equal to s squared minus 2x squared v plus v squared s squared all over x v squared s squared plus our 1. Okay, so here, this right here, we can do some factorization at the numerator. So when we do that, we are going to have x dv over dx plus v should be equal to, when we factorize s squared out, we are going to have s squared minus 2v s squared out into 1 minus 2v plus v squared all over v squared s squared plus 1. Okay, so once we have done this substitution and factorize it perfectly, we can see clearly that s squared will take off this s squared, right? So we have x dv over dx plus v, that should be equal to 1 minus 2v plus v squared all over v plus 1. Okay, so once we have this, we can still do manipulations and then bring this here. Okay, so when we do that, we are going to have x dv over dx plus v should be equal to 1 minus 2v plus v squared all over v plus 1. Okay, so we are sending the v here, so we have x dv over dx should be equal to 1 minus 2v plus v squared all over v plus 1 minus v. Okay, so this we have right here. We can spread this v here to all the terms. So we have vx dv over dx should be equal to v here times whatever is in the brackets all over v plus v, this v times 1 is v, minus v times v is going to be v squared. Okay, so we have vx dy over dx should be equal to this takes of this, so we have 1 minus 2v plus v squared. Okay, plus v minus v squared. Okay, so now we have a linear expression. So this minus v squared takes of this positive v squared. All right, so we have vx dy dx v squared dv dx should be equal to 1 minus 2v plus v. Okay, so we have vx dv over dx should be equal to minus 2v plus v is going to be minus v. Okay, so let's go here. So here we are going to have vx dv over dx that should be equal to 1 minus v. Okay, so this we have right here. Now we have only two variables, so we can separate them so easily. Okay, so we said this here, okay, we multiply here by the x, here by the x. Okay, so this takes of this, so we have vx dv is equal to 1 minus v dx, right? We have 1 minus v dx is not separable, right? It has not been separated, so we have to take this here and bring the x to this section. So we divide here by 1 minus v, 1 minus v. Okay, so this takes of this, and we have vx dv over 1 minus v over here, and that should be equal to 1 dx. But we have x here still. All right, so we divide here again by x, here too by x. So this x takes this x, and we have v over 1 minus v. The v should be equal to 1 on x dx. Okay, so now we have been able to separate the variables completely. We have been able to isolate the v and the x. Okay, so now we can go ahead and integrate both sides. So, okay, integrate here, integrate here. You know, the integral of 1 on x is ln x plus a constant, say a. Okay, so once we have this, then we now concentrate on the left hand side. The left hand side doesn't seem so easy to integrate. So here, what we do here, let's maintain it first. 1 minus v dv. Okay, so this here, we have to do some algebraic manipulations because this is not a constant. The v is not a constant that we say we are going to use partial fraction or apply ln in here. This is not a constant. So we have to do some algebraic manipulations over here to be able to integrate this v over 1 minus v. Okay, so here we can say that integral v over 1 minus v dv should be equal to, you know, v can be expressed in another way, right, as minus into 1 minus v plus 1. Okay, all over 1 minus v dv. You know why? When you expand this, you're going to have minus 1 minus minus, so it's going to be minus 1 plus v. Okay, plus 1. Now, minus 1 plus 1 is 0, and still we have our v there. So we did algebraic manipulation here. So we have minus into 1 minus v plus v, and that comes back to this. Okay, so once we have been able to manipulate this algebra, then here we are now going to separate this with the denominator. Okay, so once we have that, we can say that this can be separated as minus into 1 minus v over 1 minus v dv plus 1 over 1 minus v dv. Okay, so we have that separated here. Let's not worry about the right hand side. Let's concentrate on the left hand side. When we are done, we'll add it up. Okay, so here we can say that this, okay, this takes off this. So we have integral of negative 1 dv, okay, plus integral of what? 1 on 1 minus v dv. Okay, we know that integral of negative 1 with respect to v is going to be minus v. Okay, plus integral of 1 over 1 minus v is of course negative ln into 1 minus v. Or should we do step by step? Okay, so let me maintain this 1 over 1 minus v dv. Okay, so you know that we can let u equals 1 minus v. So differentiate both sides will be equal to negative, differential of 1 minus v is going to be negative negative 1 dv. Okay, so we have du is equal to negative dv. Okay, so we do that substitution and we have negative v plus integral of 1 on 1 minus v is u. Okay, times the v is now negative du. Okay, so you have negative here, so you have du at this junction. And then the integral of 1 on u is ln u. Okay, so we have negative v minus ln into u. Okay, so once we have been able to integrate that, then let's do back substitution. So we have negative v minus ln into u should be equal to the right hand side. We had ln into x plus our constant of integration. Over here, we have to apply some basic pre-calculus knowledge in here. But let's first do our substitution. We said u should be equal to 1 minus v. So we have minus v minus ln into absolute 1 minus v should be equal to ln into x plus a. Okay, so here, this v right here is the same as this negative v right here is the same as e exponential, which is the Euler's number exponent negative ln v. Okay, so when you bring this here, it means that we are going to have negative v is equal to e power ln v power negative 1. All right, so we'll do this manipulations. This negative ln into negative ln e power v minus ln into 1 minus v should be equal to ln into x plus a. Okay, so this we have here. Okay, we have ln common to these steps. So what we do, we can factorize that out. So when we factorize that out, then we are going to have ln into e power v minus 1 minus v, right? And that should be equal to ln x plus a. Okay, so once we have this, we apply the logarithmic law over here, the logarithmic property or the laws. Okay, so we know that if the negative is here and this side is positive, one log property is that if you have log a plus log b, then we can have log a b. Okay, so we are going to apply this property over here. Okay, so we have negative ln into 1 minus v e power v. So we apply this property in here because they are adding, we multiply, and that's what we have here. And that should be equal to ln into x plus a. Okay, so once we have this, we can see that both sides contains ln. Okay, so we can go away with the ln. Okay, so when we do that, it means that let's bring this negative to this section. So we divide here by negative ln, negative ln over negative ln. Okay, so we have 1 minus v e power v. That should be equal to when we do that here, that means that this, this is dividing everything here. Okay, so we are going to have ln x plus ln a. Okay, so we are going to have ln ax here. Okay, so 1 minus v e power v. So once we have this, so this we are going to have 1 minus v e power v should be equal to ln into ax. Okay, at this section we can the lane should go away from here because we divided the lane. Okay, so we have this equals ax. We are interested in the constant standing alone. Okay, so we will divide by x. Okay, so we are going to finally have 1 minus v e power v should be equal to 1 or c or a, they are all constant, okay, all over x. Okay, so here we can say that this is our differential equation. We have been able to differentiate it, and we have been given an initial values, right? An initial values of y into 1 equals 0. This means that y is equal to 1. Okay, so we have that here. So we have 1 minus 0 over 1 e power 0, of course, should be equal to a over 1. Okay, so we have 1 minus 0 is of course 1. 1 times e power 0 is e power 0 is equal to a. And we know that e power 0 is 1. So we have our constant to be 1. So once we have our constant to be 1, we substitute into the general solution and we get our particular solution. So here our particular solution is going to be 1 minus y on x e power y on 1 y on x is equal to our a now is 1 all over x. Okay, so this becomes our particular solution. So this becomes our particular solution. Ladies and gentlemen, thank you very much for watching. I really appreciate your time. Don't forget to press on the notification bell. I'll give you more updates pertaining differential equations. Don't forget, you can leave a comment. I'll come back. Bye-bye.